Okay, the next topic is eclipses. So first let me ask a question. What is the configuration between these three bodies for a lunar eclipse? Where's the moon, and the Earth, and the sun? What's the order? Sun, Earth, Moon. That's right. So here's lunar eclipse. Sun, Earth, Moon. And so Earth is bigger than the Moon. Earth casts kind of a big shadow. And so the Moon, if certain other conditions that we'll get to shortly are right, the Moon can move into Earth's shadow and be darkened. It's been about 100 minutes in the shadow. Anyone ever see a lunar eclipse before? Yeah, they're kind of common to see. I mean, it's a 100 minutes is perfect. Yeah, it's a great date night. You got a blanket and a bottle of wine. It's worked for me. Highly recommend it. Here's a time-lapse photo of a lunar eclipse. And I want to explain this because you'll see these here. So the moon is moving across the sky. It's moving into Earth's shadow, so more and more of it's being covered. In fact, in ancient days, this is how we knew that the Earth was round. It's not Columbus that figured out the Earth is round. That's been known for a long time. You can see it, the shadow of the Earth cast on the moon. It has curvature, so the Earth has to be round. But I point this out because, not the roundness of the Earth, but you'll see sequences of photos like this quite often in magazines and on the internet. The moon doesn't suddenly get brighter in red during the lunar eclipse. It's going into the shadow, and it's just as, it's almost completely dark. What you're seeing here is, before it's completely in the shadow, the moon is very bright. So you want to take a picture of it, it has to be a very short exposure, just a click of your camera. Because if you do a long exposure, the moon will saturate. Then when it moves into total darkness, there is a little bit of light scattered onto it. We'll talk about that in a second. Very low level of light. So if you want to take a picture of it, you have to take a longer exposure. Bring in a lot of light. And that's what you're seeing in pictures like this. The middle is really just as dark as the shadow in the other images there. But what they've done is they've done a long exposure, and you can actually see it in eclipse. And it's actually kind of cool to see. If you're out looking at it, bring binoculars or something. You look at through binoculars, I've noticed you really get a feel for the three-dimensionality of the moon. It looks not like a disk in space, but like a ball sitting there in space because of this light that's scattered upon it. So let's answer that question. Why is there any light on the moon? And that has to do with the thinness of our atmosphere. So here's Earth. That has to do with our atmosphere, which happens to be thin. The atmosphere is paper thin. Here's the moon back here in Earth's shadow, and the sun's coming from over here. Some light, most of the light hits the Earth, won't get to the moon, but some of the light will skim right through our paper-thin atmosphere. And the atmosphere scatters light, scatters blue light preferentially. So the blue light gets scattered way out, all over the place. Similar reason why the sky is blue. And mostly only red light continues on. It gets scattered a little bit, so some of the red light gets scattered down and lands on the moon. Some of the blue gets there too, but preferentially red light gets scattered onto the moon. If we had no atmosphere, the moon would be truly dark during the lunar eclipse. But because of our little layer of atmosphere, sunlight gets scattered on it. It's preferentially red light, because blue light scatters out of the line of sight more. And it's actually getting redder with time. So as we introduce pollutants into the atmosphere, they help scatter out the blue light. And so historically, the lunar eclipses have been getting redder because of the increased level of pollutants in our atmosphere. Which is kind of an interesting fact. Okay, so that's a lunar eclipse, a basic lunar eclipse. What is the configuration for a solar eclipse? Sun, Moon, Earth. So Sun, Moon, Earth. The Moon is a small body, so it casts a small shadow. It can't cover up the whole Earth like the Earth can cover up the Moon. It just casts a spot, and sometimes that spot makes it all the way down to the Earth. And here's a picture from space, from a satellite. You can see a dark spot on the Earth. And since the Moon is moving, and the Earth is moving, and the Earth is rotating, that spot moves across the surface pretty quickly. Everyone on the sun-facing side won't see the solar eclipse. You just have to be in that spot to get, in this case, a total solar eclipse. But if you're standing in a particular location, the spot will approach you, hover over you. It takes about 4 to 7 minutes for it to pass over you, and then continue on its way. The whole eclipse can last hours, but at any given spot, you can only experience the solar for 4 to 7 minutes. There's a good deal astronomers can sometimes get it. Still got to figure out how to capitalize upon this, but most of the surface of the planet is water. So the eclipse tracks tend to land on water more than land, and so you can go on eclipse cruises, and astronomers get to go free. They're explaining it. That's the thing I got to figure out how to get in on. But you go out in the middle of nowhere in the water. We can predict where the tracks are going to be very precisely. So you go out there and you sit, and over the horizon you'll see the spot coming across the ocean. They cover you up, and then you can watch it go. Kind of a cool phenomenon. Okay, so on the subject of solars, there are different types of solar eclipses. Let's go through the different types. We have, technically they're called umbral. These are the totals. We also have penumbral. These are partials. And we have annulars. Annular, which is a type of partial. I'll get back to that in a second. So in this diagram, we have the Earth, we have the Moon, we have the shadow the Moon is casting. Focus on that cone that's getting narrower and narrower as it approaches the Earth. The sun's way off to the left. And so again, if you're standing in this little spot, right here on Earth, you'll see a total where the Moon has completely covered up the sun. There's no way to see the sun. Now when that happens, you can see a little bit of light around the edge of the Moon, and that's the sun's corona. It's this diffuse gas above the solar surface, if you want to think of the sun as having a surface. Very hot gas, about 2 million degrees. It's bright. It's just not as bright as the rest of the sun, so we normally don't see it. Our eye adjusts and sees the rest of the sun. But if you cover up the rest of the sun, the eye adapts again, and you can see the coronal light. Only during the eclipse will you see that. Now, if you're not in the spot, you see there's this kind of larger spot, and this is the region where you can have partials. Imagine you're standing up here above the central spot. Well, there is some light coming from the sun. It's blocked by the Moon, but there's light coming from other parts of the sun that can pass over the Moon and get to you. And so you'll have partials. And partial solar eclipses are pretty common. The totals are very rare because the spot is small, but this spot is much bigger. So you can have a wide variety of partials during a solar eclipse. You don't really notice them. I guarantee you there have been lots of partials that happen, and unless you saw it online, you didn't even know that it happened. And that's because, if you block half the sun with the Moon, it's giving half as much light, but the eye is a powers of 10 device. So we don't really notice if the sun gets 10% fainter or 10% brighter, or if anything gets 10% fainter, 10% brighter. We notice if it gets 10 times fainter, 10 times brighter. That's how the eye works. It works on over many orders of magnitude. So if I block half the sun, you don't really notice it. It's like a thin cloud kind of passing in front of the sun. You don't pay any attention to it. There are other effects that take place during the eclipse that are more noticeable. You'll notice it get cooler during that 4 to 7 minutes of totality, or even during a partial, you notice it gets cooler. If you block half the sun, you don't notice the light change, but half the heat is gone. It's being blocked by the Moon. And you'll notice it's like moving into night very quickly, where the sun is half below the horizon, you're getting less heat from the sun. Very quickly, you're getting less heat, and so it'll get cooler. The wind will start blowing. Because under that dark spot, you have cooler gas. Around it, you have warmer gas, and warm gas tends to displace cool gas. So winds pick up a little bit. Things you might notice, but again, you probably wouldn't notice unless you knew to look. And, these things are predicted all the way out into the future, and we know when they're going to occur, but most people don't search online and find them in advance and mark it on their calendar. They find out the morning of, if they're checking the news or something, and say, oh, there's a solar eclipse today. And they say, how can I see this? And you don't want to go out and just look at it, right? The sun can damage the eyes. We talked about that before. And even during totality or near totality, you don't want to look at it. Coronal light, or as soon as it moves off, it can damage the eyes. Even if it doesn't hurt, it can be damaging. The right way to look at the sun is through a certain grade of welder's glass. I forget which grade. But if you only have a couple hours before the eclipse is going to occur, you can't find the welder's glass. So what do? Well, there are a couple of inexpensive things you can try. First one will make you look really cool. I've done this before, it works. And I looked really cool when I did it. So you get a box, and you poke a hole in one side. A small hole, pinhole. You don't want too big, it won't work. You're basically making a pinhole camera. On the other side, on the inside, put a piece of paper. Sometimes it's hard to see this on like brown cardboard. Put a piece of white paper, and then face away from the sun during the eclipse. And it will image. It's a little camera, and it will make an image of the sun on the piece of paper. And you'll be able to see the crescent and the sun being covered up or uncovered as the moon crosses across it. That's one way to do it. You can also hold it sideways on your shoulder. Back in the 80s with our boom boxes. You all remember, right? No. I remember the 80s. Here's an even cheaper way. If you can't find a cardboard box in time, run to the nearest tree. Now, it doesn't work in winter when all the leaves have fallen, but in summer or fall or spring, if you have trees with lots of leaves, the leaves cover most of the sky. And if you stand under a tree, even like not during an eclipse, and look up, you'll see little points of light coming between the leaves. Those are pinhole cameras, and they cast right onto the ground. So you just stand under a tree. If you look carefully at all the holes of light here, they're all crescents. This is a partial solar eclipse. And as the moon covers more and less, the crescents change their shape. And I've actually seen this. It really does work. So, very cheap pinhole camera, stand under a tree. Let's see, I think I got a little movie. So, here, I'll play this again. This is a movie of the moon moving across the sun. It's not a total. It's pretty close to a total. But this is a partial. Cover maybe 90%. It jiggles around as the atmosphere distorts light as it comes in, and maybe issues with the mount of the telescope, but you get the idea. Here's another time-lapse sequence. Again, they just took image after image. You can see the moon, both the sun and the moon are moving in the sky, but they're moving at different speeds. They cross each other. And there in the middle, again, they took a longer exposure. Normally, if you took a short exposure like you did with all the others, you wouldn't see anything. They took a longer exposure, bringing out the corona. You can't do a long exposure on the other ones because you'd saturate your image. The short exposures, and then when the lights are mostly off, you can do a longer exposure and see the corona. So you'll see things like this. Okay. Annular. Let's get those in here. So this is a representation of the moon's orbit. The orbit is to scale. The planet and the moon, they're not to scale, of course. We talked about that before. We wouldn't be able to see the moon in the image if we did it to scale. But the orbit is to scale. If you look at that carefully, is that perfect circle? No, it's a little bit egg-shaped. The moon's orbit is a little bit eccentric. As we'll learn in lesson 2 when we get to Kepler, all orbits are elliptical. Circle is a special case of an ellipse. And Earth's orbit around the sun is very close to circular, but the moon's orbit around the Earth is a little bit elliptical, which means sometimes it can be closer, and sometimes it can be farther away. If it's closer, the moon appears what? Bigger or smaller? Bigger. If it's farther away, it appears smaller. So here, I'll play a little movie of the sequence. Here's 1 month of moon images. I gotta open this with quick time. So you see the phase cycle, but you also notice change in the size of the moon. It gets bigger, it gets smaller. And that's because the orbit's elliptical. Sometimes it's closer, sometimes it's farther away. Now, actually, this figure right here will show the total difference. Sometimes it can be that big on the left and sometimes that small. Now, people always say to me, you know, the moon looks so big right now. Why is that? And it's not this effect. This takes 2 weeks. Over the course of 2 weeks, it goes from big to small. The next 2 weeks, it goes from small to big. You don't really notice that. The effect that you're seeing, it's normally when the moon's on the horizon, people say it's big. It's a psychological effect. Next to the moon, you have big buildings, big trees, big mountains, so you think the moon is big. It's as big as that mountain. But then when it gets high up in the sky, it's all by itself, nothing else up there, lonely, small, psychologically anyway. It looks small compared to the vastness of the sky. So the change in the size of the moon, most of that's a psychological change. But there is a little bit of a true change. That happens not over the course of hours as it rises, but over the course of 2 weeks. Well, the sun is about half a degree in the sky. It's big, but it's far away, about half a degree. The moon is small, but it's nearby, and it's also about half a degree. So sometimes it's a little bit bigger. This is 12%, but I think it really is 14%. Anyway, 12 or 14%. Sometimes it's, let's say, 12% bigger. Then it can cover up the whole sun. You can have a total. But sometimes it's smaller. It's actually smaller than the angular size of the sun, and you won't be able to, even if you're perfectly aligned, you won't be able to cover up the whole sun. And that's when you get an annular eclipse. It's a type of partial. So here the moon is farther away. The shadow of totality stops right here. You'd actually have to go into space and get in this cone to block the sun completely. Down here on Earth, it's just partials. If you get directly in the middle, it's this type of a partial. You've covered up the center, but not the edge. So this is kind of a ring partial, if you want to think of it that way. It's like a total in the sense that it's centered, but it doesn't cover all the lights. The moon is too small, at least appears too small, angular-wise compared to the sun. So here's a time-lapse sequence of annulars. It's kind of interesting to point out, they're both about the same size, and it's just because it's kind of a coincidence. The moon is moving away from the Earth, about 1 centimeter per year. We'll talk about the reasons why in lesson 6. But it's moving away. 1 centimeter per year is a good number to keep in your head. It's the rate at which the moon's moving away from the Earth, approximately. It's the rate of continental drift, approximately. It's the rate at which your fingernails grow, approximately. It's a good catch-all number. You go thousands, millions, billions of years from now, the moon's going to be farther away. It's going to look smaller. And at some point, it will never be able to cover up the sun anymore. And so there will be no more total eclipses. As we go into the past, the moon was closer, it was bigger. And all perfect alignments were totals. You didn't have annulars. We live in a time where you can have both totals and annulars, depending upon the lunar distance. A kind of interesting factoid. Okay, and here is a plot, doing good on time. Here's a plot of tracks of totals and annulars on the surface of the Earth. This goes from like 2000 to 2020, about a 20-year span. So we're done with more than half of these here. The red ones are the totals, and that's actually the shadow, where it's going to hit on the ground. The blue ones are the annulars. That's where the shadow would be, but, well, I mean, that's where you have to stand to see the annulus, the ring partial. But again, you don't get totality because the moon's too far away. And, I mean, there's one that goes right through North America, actually goes through North Carolina in the western parts. So, in 2017, I guess I'll lead an expedition to the western parts of the state. And you all, still being undergrads here, taking my class for the 7th time, you can join me, it'll be fun. Notice at the top of the map and the bottom how they get really wide. Is that real? What causes that? Yeah, the Earth is a sphere. We're making a spherical map, projecting it onto a flat surface, you get distortions. Antarctica's not really that big. Canada, Russia, they're smaller than they appear. So everything gets stretched out up there. Okay. We'll come back to this figure in a little bit.